Hello, and great to see a full hall today. And it's a very special occasion for us at ICTS, so I'm very glad that so many of you could join us for this. So let me firstly warmly welcome all of you to this inaugural P. Rajagopalan Memorial Lecture. And the occasion of the dedication of the P. Rajagopalan Visiting Chair Professorship at ICTS. These are both very special for us here. And so I'll tell you a little bit about it. And for many of you, you're probably here at ICTS for the first time. Or how many have been here before? Okay, good fraction, but not the majority. So anyway, I see now that you've been here, you know what ICTS is like. Get all your friends to also come. And ICTS does research. It does a lot of workshops in frontier areas in the sciences, in mathematics, physics, computer science, biology, and climate sciences. And we do a lot of outreach as well, including the Copy with Curiosity program, which many of you may have heard of, which we do at the planetarium every month. I think last Sunday there was a Copy with Curiosity at the Jawaharlal Nehru Planetarium. So you should tell your friends about it, and hopefully you can come for those events as well. But anyway, coming back to the occasion today, as I said, it's the inaugural lecture and dedication event for this special chair. So I'm very delighted that we have in person Mrs. Vidya Rajagopalan, who has very generously endowed this chair in the memory of her late father, Sri P. Rajagopalan. And I mean, this lecture series celebrates, I think it says it very well here, that it celebrates Sri Rajagopalan's profound love for the sciences, his spirit of innovation, and his deep devotion to India. So when Vidya and I met some couple of years ago, I think she felt ICTS might be a good vehicle for preserving this passion of her father's for science, for India and its growth. And so Sri Rajagopalan had a very long and illustrious career, which in some ways intersected with mine. My father was actually working with the late Rajagopalan, and in both of them were in public service for many years in the Indian ordnance factories. And so I feel specially kind of thrilled that we are able to honor his memory here through this chair and these lectures. So I'm also very enthused that we have the inaugural chair holder, Professor Subir Sachdev from Harvard, and who will give the inaugural lecture in the series. And I think that that sets a very high bar for this. I'll introduce Subir to you a little later, but as all of you know, he is one of the very distinguished scientists today in the area of condensed matter physics. But let me first say a little bit about the chair itself. What the special P. Rajagopalan chair will do. It enables ICTS to host distinguished scientists like Subir from around the world for a period of a month in the course of a year. And this is something that's invaluable for the research community at ICTS, and including, of course, our faculty, students, postdocs. But another novel aspect of this chair is that it enables collaborators and visitors from other institutions in the country to also come to ICTS, and thus benefiting the nation's scientific efforts at large. So I think this is a way in which ICTS can play a very effective role, truly as an international center, bringing some of the world's best scientists here to interact with our research community, and hopefully many of you in the future as you develop into scientists. So, and as I said earlier, I'm very confident that with the high bar we have set, with Subir, we'll have a stream of distinguished scientists enriching the atmosphere here as the holders of this very special chair. I'll now invite Mrs. Vidya Rajagopalan onto the stage to say a few words, but I want to also briefly introduce her. She's a very distinguished engineer herself, who is currently the Senior Vice President for Electrical Hardware at Rivian, and she has built semiconductor products ranging from the first 0.75 micron alpha processor at the DEC, the Digital Equipment Company, to the 16 nanometer Zinc family of at Xilinx, and she serves as a member on the board of visitors of the University of Maryland's James Clark School of Engineering, and she has been Senior Director of Engineering at Tesla from 2017 to 2019, and before that at Silicon Graphics and many other very well-known names in the semiconductor and digital industry. So it's a particular pleasure to welcome her into the ICTS family in some sense by having endowed this. And so Vidya, please.
Thank you, Rajesh. I didn't think you were in marketing, but you did a great job of promoting me. So it's an honor to be here today amongst this very erudite audience. I walked around the hallways and I couldn't understand anything on those chalkboards. So I'll hope Subir will be able to explain some of that to us later today. I know you all came here to listen to Dr. Sachdev and not to me, so I'll keep this very short. Because this lecture series is named after my father, I thought it would be appropriate to share a few words about the man behind the name. Born in 1926, my father started his career around the time of India's independence. Like many colleagues from that generation, he was inspired by the nation's founding leaders and was deeply committed to India's future and success. He spent the majority of his adult life at the Indian ordnance factories dedicated to ensuring that an independent India was self-sufficient. While he rose to the rank of chairman of the Ordnance Factory Board, he was always really most known for his simplicity, integrity, humility, and the kindness and respect with which he treated people. But I would really be remiss if I did not mention his insatiable curiosity and love of learning. He never stopped learning his entire life. He graduated from the Guindy College of Engineering in Chennai with a degree in electrical engineering and started his career immediately after. Yet he felt that to be a truly good engineer, he needed to understand another domain. So he earned a second degree in mechanical engineering through the AMIE distance learning program by studying after hours. His love of learning went far beyond science and technology, though. Growing up, I remember my dad going to night classes to learn languages, eventually mastering German, Russian, and Spanish. It was often said that when he negotiated international agreements, his foreign counterparts were hamstrung by the fact that he understood exactly what they were saying in their own local language. Later, upon the advent of personal computers, he went to evening classes to better understand that technology. And when he traveled internationally, he would bring me back not chocolates, but electronics and chemistry gift sets, eager to expose me to hands-on learning. Upon retirement, he moved back home to Chennai. But even in retirement, his curiosity never waned. I was reminiscing last night with my cousin Amrit, who may be in the audience today, about how my father would visit him in his hostel at IIT Madras just to borrow his class notes. Mind you, this was after he had retired. He wanted to see how physics and engineering were being taught in the 1980s compared to how he had learned back in the 1940s. If he had one hope for his children and grandchildren beyond health and happiness, it wasn't for wealth. It was for them to possess a deep, lifelong love of learning. He would even joke with them to remember to take a warm coat to their future Nobel Prize ceremony. It is profoundly fitting, therefore, to honor him with a lecture series because he never truly stopped being a student. My mother, Mrs. Rajagopalan, my sister, Sai Sri Raghunath, and all of our families are deeply grateful to Dr. Sachdev for taking the time to be here today, and to Dr. Gopakumar, and ICTS for instituting this wonderful lecture series. Thank you.
So now we move to the main lecture, and let me introduce the speaker a little more formally. So Subir is an old friend of ICTS and has been involved from, I think, over 15 years probably with ICTS in many aspects, including being very importantly on the International Advisory Board, which has helped to guide the academic growth of ICTS and been a champion for ICTS elsewhere in the world. And I think Subir is, I think he is so often back in ICTS that it feels like it's just little small intervals between his visits. But this particular chair, I think, enables him to spend a longer period at ICTS, and already some of his collaborators from elsewhere are also coming here, apart from the collaborators he has at ICTS, which includes one of our latest faculty members, Avishkar Patel, a recent graduate from Harvard who did his PhD with Subir. So this, I think, was this chair helped us to have Subir's engagement even deeper than it has been already. So Subir is currently the Herschel Smith Professor of Physics at Harvard. He attended high school in Bangalore, and that's why we have people from St. Joseph's here. And he's actually even going back to the school tomorrow. He completed his first year at IIT Delhi and then earned degrees, his undergraduate degree at MIT and PhD at Harvard. He's a member of the US and Indian National Academies of Sciences, a foreign member of the Royal Society, and he has received numerous honors, which include the Dirac Medal of the International Center for Theoretical Physics in Trieste and the Larson Saga Prize of the American Physical Society. And today we'll get a little glimpse of his transformational work in the theory of quantum matter and phase transitions, where he's also the author of two of the classic textbooks in the topic. In fact, the latest textbook was based on lectures given during the pandemic or just after the pandemic, I think, partly here and partly at Princeton. So it was very nice to be actually associated. And we have in our library a signed copy from Subir of his latest textbook. So in any case, we'll hear from Subir about about quantum entanglement and the mysteries of quantum entanglement, which connect things which seem apparently very distinct, namely superconductors, specifically high temperature superconductors and black holes. And this has been one of the signatures of his work that has significantly deepened our understanding of strongly correlated electron systems, including these high temperature superconductors, and creating these very unexpected connections with quantum theory of black holes, Hawking radiation puzzles thereof in quantum information. So let me invite Subir over so you can have your treat for which you've all been waiting. Thank you very much.
Okay. All right. Thank you very much, Rajesh, for that very kind introduction. Of course, you're right. It always feels like I'm coming back home when I'm coming to ICTS, especially since I grew up in the east part of Bangalore near Krishnarajpuram. And it's also wonderful to see some boys and girls from St. Joseph's Boys High School. In my time, it was only boys. And I was terrified of speaking to girls. And also from KVASC, Kendriya Vidyalaya, where I spent 1 year before going off to IIT. So thank you all for coming. And I'm sure you'll have many questions as I go along. And people keep saying this is way too complicated for me. Well, I hope I'll try to simplify it, but not make it, not dumb it down. I will talk about the real thing, I hope. And maybe at the end, there'll be plenty of time for questions. And I also want to thank Vidya Rajagopalan. Thank you very much for your wonderful gift. It's an honor to be here, especially in honor of your very accomplished father and also in honor of your accomplishments. So, all right. So this is about, as Rajesh said, from superconductors to black holes. But the main theme that ties them together, as I hope to show you, is quantum entanglement. Quantum entanglement was a concept that emerged in the 1930s from Einstein's objections to the theory of quantum mechanics. And it was a philosophical puzzle. And it's moved from that to being really at the center of many, many developments in modern physics. And I'll try to introduce some of them to you. But that's not how I started working on this. I started working on this by just thinking about what seemed like very little boring problems in the study of some material. Some chemist had made something in their lab, and we wanted to understand it. So that particular material was a superconductor. So what's a superconductor? Well, almost any metal, if you make it cold enough, it becomes a superconductor at some point. So for mercury, this was the first discovery by Camerlionis in 1911 in the Netherlands, where if you cooled it below this very low temperature, electrical current could flow in this material with strictly zero resistance. So that sounds exciting. If you can transfer current with zero resistance, it surely has many applications. The only trouble is it requires this very, very low temperature. And achieving this low temperature requires this refrigerator behind Camerlionis, which takes up a big room. And even today, that's the case. If you want to go down to such low temperatures, you need a big, huge refrigerator. So it was sort of a sidelight, not of much excitement, except for people who worry about such things, but not in the general public for sure. So all of that changed in 1986, when I was just starting out as a researcher, when a whole new family of materials were discovered by Bednorz and Mueller, for which they got the Nobel Prize just the next year. The most famous of which would be yttrium barium copper oxide. Has a very complicated crystal structure, complicated enough to scare away any physicist, especially the string theorists. This is just way too complicated. But it's just a little ceramic. And if you take this little pellet, you can hold it in your hand. All you have to do is dip it in liquid nitrogen. That's what's been done. And here's a little pellet of it. And this is a track of magnets. Then, it's a superconductor and it floats because it can carry currents that repel the magnetic field very easily. At some point, it drops down. Well, that's because it's become hot. You just have to keep it cool. So all you have to do is just keep it cool below liquid nitrogen. And liquid nitrogen is not that expensive. It's something any classroom can have. So you could imagine you could have underground cables with liquid nitrogen with this wires of WebECO in them and transmit huge amounts of current and power without loss. So that's an application that's actually just starting to come online. China has a huge factory now making cables of WebECO. Let's see. But one particular application that's already becoming quite important is the use of these magnets for compact fusion reactors. So because these are such good conductors of electricity at such reasonable temperatures, and you can also make big whole wires of them, several kilometers long, which you wrap them around to create a magnet. And inside here, you're going to confine a plasma that's going to create energy. Anyway, so this is a way of getting plasma fusion. And optimistically, as this company's website says, it's the surest path to limitless clean fusion energy. All right, I'm not sure I want to believe that yet, but certainly these materials are not transforming fusion research. And the whole new generation of fusion reactors, I think, will be coming online in the coming years. And in fact, not just this company, these companies around the world. There's one in Bangalore called Pranos. They came up with this acronym MAGA for magnetic gain. I'm sorry, coming from America, MAGA is not something, not the best choice. But anyway, okay, so this is a company which is just across the highway here in North Bangalore, near JNC ASR, which is making, again, fusion reactors, similar types, I think. And I asked ChatGPT how many are there companies in China, and it listed 4 of them, okay, that are doing exactly, taking YBCO and making fusion reactors out of them. Anyway, so this is an emerging technology. No, it's 40 years since the discovery of the material. It takes a while. I mean, the main obstacles now are engineering obstacles because you have to make long wires and keep them stable and so on, but let's see. Okay, so I'm not an engineer, really. I ask basic questions on why is it that YBCO, as opposed to another material, has this remarkable property. I mean, it remains true that today there's no other material that can beat YBCO or other materials in this family. It's still by far the best, 40 years later. So the hope is that fundamental understanding will allow us to find maybe better materials or more appropriate materials that technological leads to ban. But that's not what's driving me. What's driving me is, can we understand, what is the basic physics of it? What is the underlying quantum mechanics, ultimately, that leads to these remarkable properties on the macroscopic scale? So, why do the cuprates become So these families called the cuprates, sorry for that buzzword, cuprates because they have copper in them. Why do they become superconductor temperatures higher than the boiling point of nitrogen? And are there even other temperatures? So these are big questions, which if you finally answer them, surely will make that person a celebrity. So I would say over the last 3 decades of work, we haven't completely answered them, but we're getting somewhere. And I want to give you some idea of the progress that's been made. But one of the remarkable things that's happened is that we were asking some very simple basic questions about these materials, but that's led to a much deeper understanding of many body quantum physics, what happens when you think about the quantum physics of trillions of electrons. And that's had an impact on many other aspects of physics. I'll give you a flavor of that in the theory of black holes. It's also had an impact on theory of quantum error correction and quantum computing. I won't say anything about that. Okay, so let's go back to basics. How do you connect quantum mechanics to a material like YBCO, which we now call quantum materials? All right, so quantum mechanics had its origin in something very simple, in understanding the structure of the hydrogen atom. So Newton taught us that Newton's laws apply when the Earth moves around the sun or the moon moves around the Earth. So the question you can ask is, how small can you make it before Newton's laws don't apply? So Newton showed it also apply to the apple and so on. But when you get down to an electron and a proton and a hydrogen atom, those laws do not apply. And there's an entirely new theory which is really needed at these small scales, which is the quantum theory of Schrödinger and Heisenberg. And one of the consequences of this theory is that hence the word quantum, that the orbits of the electron are quantized, that they're only in some very select orbitals. These are the 1s, 1p, 2s, 2p orbitals that you may have heard about in chemistry. Those can all be derived from Schrödinger's equation. All right, so that's the quantum theory of one electron. But we are interested in the quantum theory of 10 to raise to the power 23 electrons. That's really the question the whole field is working on. So very soon after Schrodinger's work, Sommerfeld, sorry, it's okay, made a very bold proposal to understand the behavior of electron in a metal, like copper or gold or anything that you might find in a smartphone. And he made a very simple assumption that the electrons, again, occupy orbitals, just like a single electron occupies orbitals in hydrogen atom. But these orbitals are now plane waves. They're just waves with different velocities moving through the crystal in both directions. And they're basically free plane waves, and they're largely independent of each other. But they do obey another important principle you may have heard of in chemistry, which is the exclusion principle, that you can't put two electrons in the same orbital at the same time. So particles that obey that are called fermions, and particles which don't are called bosons, but I won't talk about bosons today. And so this is all he said. Let's take this very simple model of free fermions moving in plane waves in a crystal. And this theory has really been incredibly successful. It's really the foundation of everything in the semiconductor technology. It describes metals and semiconductors. There's a few bells and whistles having to do with the periodic potential of the crystal structure. But apart from that, the theory is essentially what Sommerfeld wrote down. And this understanding was essential to the technological revolution of the 60s, 70s, and 80s. It's how all the materials that are inside your smartphone work, building on essentially the Sommerfeld theory. And it's what, of course, many brilliant physicists have contributed over the years, but the central idea was already there in 1927. And this is the central idea written here. Okay, so this has been incredibly successful and now is everywhere. But when you get to the cuprates, people quickly realize Sommerfeld simply did not work. And the key assumption that Sommerfeld made was that the electrons are essentially independent of each other. So you can't think of them one by one. You have to really think of them collectively. And the collective behavior, it turns out, maybe understanding better today, involves a subtle property of quantum mechanics called entanglement. So we have to understand entanglement better to better understand these materials, and actually many other materials that have been discovered since then. And that's been the focus of a lot of quantum matter research over the years, over the past couple of decades. And I was lucky that when I was starting out in '86, this field was just starting. Nothing new, nothing was known about many particle entanglement in a metal. So that was a great stroke of luck, I think. Or maybe also I had the right intuition that this is what I should do and not string theory. But in the end, I ended up doing some string theory too, as I'll show you. So I'm just making some jokes, okay? Sorry. At Harvard, they would kick me off the stage at this point. All right, so what we have to think about is what is quantum entanglement? And we're going to build up quantum entanglement, starting from entanglement of 2 particles to 6 particles, and eventually to infinity, which is where we want to get. All right, so first of all, what is quantum mechanics? Well, I told you it was Schrodinger's equation, but really underlying Schrodinger's equation is a very fundamental principle called the superposition principle. That's really the heart of what's new about quantum mechanics. It's a principle that does not exist in Newtonian mechanics. So the famous illustration of that is the famous double slit experiment. If you send an electron, it seems to come one by one. Each electron comes one by one. But if you look at the distribution of electrons after many, many electrons, it looks as if it's a bunch of waves coming out of both slits. So you're not sure which slit did the electron go through. And the answer, of course, is it went through both. So the way you reconcile that, you postulate a new principle. And the new principle is the superposition principle. That's the starting point of quantum mechanics. It's just a postulate. I can't logically derive it for something. It's where the pioneers of quantum mechanics, after looking at many experiments, including this one, formulated this as the key new idea. So mathematician would never postulate this. It's something that came from physics. And why is it this way? I don't know. This is how the world works. Uh, and no one's ever observed any violation of this principle in any experiment since. So the principle is the following, that there are two physical states of the electron. One physical state where it's on the left, and the other physical state where it's on the right. And a third possible physical state is when it's both. You can add them and then you can actually subtract them and put various numbers here. But there's a whole bunch of superposition states that are also possible states. So it's not sufficient. In Newtonian mechanics, all I have to tell you is what is the position and the velocity of the electron. Here I actually have to tell you much more. I have to tell you which particular superposition it is in to fully specify the state of the electron. Okay, that's really all you have to expect. And everything I'm going to talk about is all about the amazing consequences on the macroscopic scale of this basic principle. All right, so let's apply to two electrons, which is what Einstein, Podolsky, and Rosen did in 1935. They thought about, Einstein said, this is all great, superposition, maybe it works, but it's got to break down at some point because it predicts something ridiculous when you take it to long distances. And he came up with this thought experiment. Imagine you had two electrons, say in a hydrogen molecule. So I've represented each electron by an arrow pointing up or down. That's simply representing one particular feature of the electron, its spin on its own axis. So one possible state is that the left electron is up, maybe spinning clockwise, and the right electron is spinning anti-clockwise. Another possibility is the opposite assignment. And what we do know, and by this time in 1935, we knew from lots of experiments and theories that in hydrogen molecule, the answer was it's both. It's up, down, minus for strange reasons, down, up. That is the actual state of every hydrogen molecule. It's a superposition of two possible states of the two electrons. All right, so maybe that's correct. Well, no, Einstein conceded that's correct. But he said, okay, suppose you could do an experiment where you remove these two particles far apart without disturbing their spin. And today you can do such things for, at least for light, not for electrons, but quite easily. Then this electron could be with me, and the other electron, could be in China. And if you've done it carefully enough, they're still entangled. So you have this non-local structure now between an electron with me and an electron in China, and they're entangled so that when my electron is up, the other electron is down, or vice versa. So he said, well, this leads to a contradiction because by quantum mechanics, I can now look at my electron. And when I look my electron, quantum mechanics says, by the measurement postulate, I will see either up or down. I will not see both. So say I see up. Then, but if you look at this quantum state, if I see up, then instantaneously it must mean that the other electron in China is down. So I have had, what Einstein calls spooky action at distance. By measurement here, I have changed what's the state of the world in China. And he said, this is surely not possible. And in fact, and I wondered, in fact, he actually did see exactly this. This is a letter from Albert Einstein to Max Born in 1947. I cannot seriously believe in it being quantum mechanics, because the theory cannot be reconciled with the idea that physics should represent a reality in time and space, free from spooky action at a distance. All right. So as was usual with Einstein, he is brilliant. He identified the key physical content of quantum mechanics when it comes to more than one particle. But despite his unease, he should have believed in it because it is completely true. These kinds of experiments have been done, not precisely this one, but related ones. There's absolutely no question that this actually does happen, that there is what he calls spooky action at a distance. But it's not really action at a distance. That's where I think he had slight misconception. I wouldn't say misconception. He didn't get it quite right, because even if my friend in China measures something, I don't know what he measured. He doesn't know what I measured. He doesn't know what he measured. He doesn't know what I measured. I don't know what he measured. He would have to call me and tell me what he measured. And he would say, I measured down. I would say, I measured up. Oh, everything's great. But that communication will take some time. So before any information can really transfer, the information transfer is limited by the velocity of light. So there are philosophical ways of reconciling this with relativity and locality, and also very practical ways. You have to take a very practical point of view. All right, so moving to 2, there's 6. So that's for 2 electrons. That is indeed how electrons entangled in a hydrogen molecule. Okay, so 6, actually we go back to 1865 with Kekule, who this was way before the discovery of quantum mechanics. Quantum mechanics was discovered 100 years ago, in 1925-26. This was way before that, in 1865. He came up with the theory of, he was a chemist, and he came up with the theory of benzene. Apparently has a daydream of a snake seizing its own tail. So benzene has 6 carbon atoms, and the carbon atoms have double bonds between them. Here I represent the double bond by an ellipse. So this is one configuration of double bonds, and this is another configuration of double bonds. And if this was the actual structure of benzene, then benzene would not be a perfect hexagon. These bonds will become a little smaller than that bond, and it will be some distorted structure. Anyway, I don't know if chemists knew that benzene was well, benzene is a perfect hexagon, no question. So which is it? And he said, well, it's both. He called it resonance. It resonates between this, and it's really both. And of course, what he had discovered was a form of quantum entanglement. This is how we'd say it today. Each double bond is actually just the EPR pair of up, down, minus, down, up. And so you form this entangled state of 2 electrons, and then you have a higher level of entanglement of 6 electrons. Okay, so that is what Kekule discovered. Was a very early discovery of many particle entanglement. And it clearly affects very physical properties of the benzene molecule, which you can measure and check. Okay. All right, so now we want to go from 2 to 6 to infinity. And that's where my favorite model comes in. So this model, I came up with some version of it soon after the discovery of the cuprates, because it was becoming clear from many experiments that Sommerfeld's theory is a total failure. And entanglement, the word entanglement wasn't really in vogue in those days. But what we called entanglement then was really, we had to really think about this in a more sophisticated way of many particle states that are not just some simple extension of Sommerfeld's state. And that seemed like a really hard problem. So I said, okay, I don't care about the real crystal. Can I write down any state which has the basic features of what's being seen in the experiments? I don't want to really know where every copper atom is, where yttrium is, and all the little details. Just going to play around and find something that captures the essence of the electron entanglement. And luckily, I think I came pretty close to the real world. All right, so I said I also have to come up with a spooky dream. And so one way to think about it, particularly thought about snakes eating its own tail. I thought about snakes in the game of snakes and ladders, where you could think of each snake as an entanglement between 2 electrons. All right, so that's one way to remember what the SYK model is. So here's specifically this is the precise definition of it. You take a bunch of sites, positioned at random, and each site can absorb 1 electron. So say this is a trap in some crystal where an electron can go. So the electrons occupy these traps. So this is one quantum state where all the electrons are sitting in these particular traps. But now we want them to move around. And in quantum mechanics, this is a process of tunneling. Electrons will hop quantum mechanically from one side to the next. All of them will move around, and The correct state is a superposition of all possible motions of all the possible electrons. That's, of course, very hard to solve. So we made a small restrictions. We don't allow each electron to move on its own. If you did, you'll be back to Sommerfeld's state. We said, okay, don't only allow the electrons to move together in 2s, 3s, 4s, 5s, whatever. So let's take the 2 case. So for example, electron on side 11 and 12 could hop, move together to sides 5 and 14. So that's one particular motion of the electrons. And in quantum mechanics, each such motion is associated with a complex number. So that's what this complex number is. And so on. So for every quantum mechanics, anything that can happen does happen. So you allow for all possible motions, each associated with some complex number. So what you really have to do now is to take all these complex numbers, feed them into Schrodinger's equation, and solve them, and that'll predict the future of this collection of electrons, of what they're going to do. Unfortunately, that's way too hard, because the number of possible states is exponentially large. No computer today could solve that for a large system. But what we discovered in 92, 93 was that if you made a simple assumption that these are quasi-random numbers, they're independent random numbers, that you could, in the limit of large number of particles, you could solve this. So it was one of those contradictory things, that making something random actually gives you more information on its eventual structure. In this case, that works because the entanglement of the electrons is very, very complicated and chaotic. All of these processes happening at the same time, and this complicated chaotic state you get finally turns out to be many-body electron state, for which Sommerfeld theory fails completely. So the whole purpose was to make somebody else fail. And that's what we were doing. Because Sommerfeld have been so successful over the past 60 years in describing just about everything. So we had to, finally we were happy we came up with something that we could solve, where Sommerfeld simply we could prove did not work. Okay, so that's basically it. It's a solvable model of multi-particle quantum entanglement. And then we could study it and look for what are some of its properties. So it turns out, first of all, the electron, which is hopping around, when they all get entangled, you get this quantum state. Now, if you disturb it, try to pass some current, you normally in Sommerfeld's theory, that would mean some of the electrons will move. You'll see the electrons moving, and that's how current would flow, by the electrons moving. But here you find the electrons essentially cease to exist. It's the whole entangled state that's going to move. There are no fermions or bosons or anyons, and the current is carried by an entangled quantum soup. All right, those are just words for some rather precise mathematical properties that you can prove for this model. But another thing we found, which, and also this was a bit later work by my colleagues in France, was a remarkable property that made us even more excited. So you can ask a question. You have some set of many particle system, and you dump some heat into it, or you shine some light, or you have a coffee cup and you stir it. You put some sugar in it. Eventually, it'll come to rest in some thermal equilibrium state. So you ask, how long does it take to relax to some equilibrium state? Now, in Sommerfeld's theory, that's actually quite a long time. It diverges as temperature goes to zero in some strong way, which has been measured in numerous experiments. And we found here that, in fact, the time is this time now people call Planckian time. So this is my main equation of this lecture that I want you to remember. Planckian time is the Planck's constant, h bar, divided by the temperature. This is temperature measured in degrees Kelvin. Temperature is really a measurement of energy. Kb is Boltzmann constant. It's just a constant because we insist on measuring temperature in degrees. So forget Kb. If you measure temperature in units of energy, this is all it's h bar over temperature. And the remarkable thing about this relaxation time is that it's independent of what this u is. Now, there was this u over here. It doesn't matter what the u is. It's universal. And this is also not something that Sommerfeld's theory ever gives you. In Sommerfeld's theory, the strength of the relaxation time of an set of electrons depends on the Coulomb repulsion between them. You need to know the strength of it. You need to know the density, and that comes in a fundamental way into what the rate is. Here, it seems to depend on nothing. Okay, so that was very exciting. And this is faster than anything else anybody had found. So so you could say that this SYK model is a champion of becoming chaotic as fast as possible. It completely loses memory of its initial state in the fastest possible way of any physical system. And the fact that there's such a bound was something I said in my book way back when. Excuse me, what's going on? Yeah, can you hear me? All right, sorry. Okay, so why were we excited when we discovered this property? Well, as I'll show you in a bit, this property is shared by some other physical systems. In fact, both the physical system and the title of my talk. The high temperature superconductors and black holes also obey this remarkable property. And so then we knew by 1999 that we were onto something really interesting. It took a while before the rest of the world believed us, but anyway, so give us a head start. All right, so let me then turn to black holes. What has this got to do with black holes? Well, black holes also fundamentally have a certain quantum entanglement built into them. First of all, what's a black hole? Black hole was theoretical discovery from solving Einstein's equation of gravity, and where you've made it a mass m very dense, made it smaller than this radius r, where g is Newton's constant and c is the velocity of light, then once you have such a dense region, this inside of the black hole is forever lost to you, and nothing can ever escape, at least in the Newtonian Einstein equations. And so this is extremely dense. If you put the Earth's mass in here, you will get a radius of 9 millimeters. So you would have to shrink the Earth down to the size of a pea to make it into a black hole. Sounds ridiculous, but amazingly, there are now black holes everywhere in our universe. There's a supermassive black hole at the center of the Milky Way galaxy and so on. These are recent discoveries in the last 15 years or so from gravitational wave observations and many other approaches. Okay. Anyway, that's all great. It's a whole different field of physics. But Hawking, Stephen Hawking especially, kind of started to think more about quantum mechanics of black holes, even before there was well established that black holes exist in our universe. So you can imagine this thought experiment, which is the same as the Einstein experiment, where instead of separating these two electrons between here and China, I put one of them inside a black hole and one I keep with me outside. I'm safely outside the black hole. I have one half of an entangled qubit, entangled pair of electrons, and the other falls into a black hole. Well, there's nothing special about the horizon. So in fact, even the black hole horizon, by the principle of quantum mechanics, can disrupt the entanglement. So it's possible. So there is some very subtle sort of quantum connection between the inside and outside of a black hole, which was not present in the Einstein-Newtonian theory. You can have entanglement across a black hole horizon. So what this means is that if I am here and I have this, I happen to look at my electron, I see it's pointing up. Well, to me, this electron is just randomly up because unlike my previous experiment where I could call up my friend in China and find out that he had a down electron, now there's no hope for me to ever communicate with the person, with whatever's inside the black hole. It's gone forever. So this particular electron is effectively random. And what we learned from thermodynamics is that randomness is what gives you temperature. So this is a very crude way of simplifying Hawking's brilliant argument that black holes in quantum theory have a temperature and also an entropy. There's a certain randomness, entropy, which counts the randomness of the black hole. In fact, more than that, Hawking gave an answer, a number for the entropy of a black hole. This is Hawking's famous formula. This is the area of the horizon. Again, other constants you've met, velocity of light, Newton's constant, Planck's constant. In fact, this was the first non-trivial formula which combined Newton's gravitational constant and Planck's constant in one physical expression. All right, so the remarkable thing about this is that it's proposing the area of the black hole. And this is not true for any other physical system. Yeah, so since Hawking told us that black holes are at thermal equilibrium, they have a temperature, we can ask, what is their relaxation time? So this is a question I asked somewhere in the early 2000s. And you can just look it up. And in fact, the formula for the relaxation time of black holes, which is something called a quasi-normal mode time, was first computed by Vishveshvara, who was a scientist here in Bangalore in 1970, before Hawking's work. But if you combine his result with Hawking's result, you find that the ring down time, or the thermal equilibration time of a black hole, which is, here I have two black holes merging, and this is like the last possible bit. They're going to become a perfect sphere, and the last bit before they become a perfect sphere is the time we're talking about. That time turns out to be Planckian. So black holes, in fact, must have, therefore, some very complex entanglement, because only complex entanglement can give you, of the type of the SYK model, can give you such short relaxation times. So that was really the start of a whole field of research, if I may say so. So this picture that people may have drawn before is not quite correct. This is a better picture. The entanglement on the black hole horizon is more like the SYK model. It's not a pairwise entanglement. It's a much more complex chaotic entanglement. And that approach gives you not just the entropy correctly, but also the Planckian dynamics that's observed. And this is something I suggested in this paper, and I talked about certain mean field gapless spin liquids. Okay, this is what's called SYK models now, after Kitaev really cleaned up this whole thing and made it a real theory of black hole dynamics. All right, and from this, many things have come about. I'm sorry, I don't want to throw this complicated formula at you, but what we have learned, just read the top, has led to a determination of the density of low energy quantum states. So for example, in hydrogen atom, there's a 1s state and there's a 1p state and so on. So you can count how many states there are in a given energy interval. So you can ask the same thing about black holes. How many states are there in some energy interval? We finally know the answer. And since the answer is somehow associated with my name, I'm showing you the formula. Okay. All right. So now, how much time do I have? I have about 15 minutes if I did this right. Perfect. So now let's go back to what started this all, for me anyway. I told you, this was really an unexpected gift. I didn't know anything about black holes in 1993. I slowly learned more about them. And as I learned more about them, I realized that my little model had something to do with them. But my aim always was to go back and solve the cuprate problem. I don't think we're there completely yet, but I want to show you in the next few remaining minutes what we learned about SYK. So what we learned about SYK has clearly taught us a lot more about black holes. I think Rajesh won't contradict that claim, I hope, or Spenta. But has it taught us more about superconductors? Well, I claim it has, and that's what I'm going to try to give you a flavor of. But this is going to get a bit more technical. I'm really going to the nitty-gritty of some relatively recent work. Okay, so this is the famous phase diagram of these cuprates. So now we have to really know a little bit more about the chemistry. So it turns out this particular crystal has a square lattice of copper atoms. So fortunately, that's really all you have to worry about, is the density of electrons in that layer of copper sites. And this is a measure of that density. And as you vary that density at a certain density P, you get a critical temperature here of a superconductor that's close to 100 Kelvin. The boiling point of liquid nitrogen is 77 Kelvin. So that's great. This is what everyone's excited about. And why is this temperature, where this superconductor turns into a metal, where the superconductivity disappears, why is it so high? That's, of course, the question. Well, if you're ever going to answer the question, we have to know what's above it. What is it going into when you raise the temperature? Well, it turns out if you look on the right, you get a very ordinary metal where Sommerfeld would be perfectly happy. And everything is conventional, looks like copper or gold or silver or anything like that. But that's not the interesting region. The interesting region is here, this white region. And in that region, you get what people have somewhat unimaginatively called a strange metal. Strange meaning, forget about Sommerfeld and everything else that followed from it. Something strange is going on. So what's strange? So there are many things that are strange. And if this was a conference on cuprates, I would spend the next 2 hours describing all the strange things. But let me just mention one of them, which is the main theme of this talk. People can measure, again, the relaxation time by certain light reflectivity measurements. You put a little piece of superconductor here, and you affect light of it. And by analyzing what you measure, you can read off this quantity. OK, so I'm simplifying here a little bit. But what you find is amazingly h bar over kT. So that's really the unifying theme of this talk. Black holes and the strange metal have this universal Planckian relaxation where the rate, how fast it becomes a thermal state, a black body, is independent of almost everything. It's the same in many different materials, which have very, very different lattice constants, very different chemical compositions. It doesn't matter. In the strange metal, this is what's universally observed. And this was also true for the SYK model. Now, of course, no one will believe me, say, OK, SYK model describes this, because the SYK model was this random set. There was no lattice, there was no square, there was no geometry to it. Here, there's a lot of subtle structure that I have to put into my theory. And that's what we've been working on. All right, so what is the approach that I think is the best, which has yielded some success in recent years? It's the idea of quantum phase transitions, as I mentioned over here, which is also the title of my first book. So what is a quantum phase transition? Well, you all know about thermal phase transition, which is like water boiling to steam. There, it's the thermal agitation of the water molecules that causes a phase transition from liquid to gas. So similarly, you can ask, can the quantum uncertainty principle can change the configuration of the electron at zero temperature? So all the uncertainty is due to quantum mechanics, not due to thermal agitation. Can that lead to phase transitions between different quantum phases, which are as different as water from liquid from gas or solid? Well, in fact, in this phase diagram, there is a phase transition. That's down here. Oops. That's down that orange circle. And it's a phase transition between this AF insulator. What is the AF insulator? Well, now these are the copper atoms. And remember, I told you they form a square lattice. It turns out we know from various experiments that the spins of the electron, there's one electron on each copper, and they form this checkerboard pattern, like a chessboard, where the black squares have electron pointing down, and the white squares are pointing up. That's what we call an anti-ferromagnet, in contrast to a ferromagnet like iron, where all the electrons will point in the same direction. That's how you get ferromagnetism. But in some materials, you get the exact opposite. It's still a type of ordering. It's a distinct phase of matter, where the spins are in this checkerboard pattern. So this is not so easy to detect macroscopically like a ferromagnet, but you can do lots of experiments that tells you this is the case. So if you look down here, there is indeed a quantum phase transition between this insulator and the superconductor we want to study. Does this, is the secret to the strange metal and this high TC hiding in this critical point? It seems rather ridiculous, at least for this material, because this critical point is very far away from the most interesting region, which is here. Okay, so why am I proposing this? Well, it turns out that in many other materials, not as good as the cuprates, here's a very complicated phase diagram that I won't even try to explain. In this other material called barium, iron, whatever, it's called a pnictide. In this material, the connection that I suggested seems clear. So here's this quantum critical point, which is a quantum phase transition between an antiferromagnet and a superconductor. And it's right in the interesting region. It's in the region where the critical temperature is high, where you've got this strange metal, this red region. So for this material, that seems like a good starting point. And a lot of people have worked on this point of view, and it has led to some successes. But this point of view doesn't seem to be right for the cuprates because the phase transition is really nowhere near the interesting region. So a few years back, we postulated that there is actually a kind of a hidden is that better? Yeah, maybe it's my tie or something. Okay. No, it's okay now. I'll just look up. Maybe if I look down, it does something. Okay, so, right. So we postulated that there's actually this pink region is a whole new phase of matter, and that there is a hidden, but the difference between this metal and this metal is very subtle. And in between, there is actually a quantum phase transition. Then everything would work because then the strange metal and the high TC would be right there. All right, so these metals differ in some very subtle patterns of entanglement, which I'll say a little bit about in the very end of my talk in a few minutes. And there's a whole bunch of recent experiments that actually support this proposal that we made about 15 years ago. Anyway, so where does this tie together? How do I get the tau relaxation, which is the key property of the strange metal? Well, so you can get rid of the superconductor and focus on this phase transition between this strangely named pseudocap metal and the ordinary metal at 0 temperature, above which is this fan, which is giving you, hopefully, a strange metal. Or in the other material, there's something else here. So is this a universal picture of these strange metals that you found in hundreds of materials today? And so this is something we've been working on quite a bit for almost a decade, and worked with Avishkar Patel recently. We think we've had some success. We've been able to show that if you account for impurities, that this position, some materials are here, some regions of the sample are a bit disordered. Once you account for that, then there is a generalization of the SYK model that does what you want. So we deform the SYK model, but we don't throw out the baby with the bathwater. We still retain the tau relaxation. And we get, as a bonus, lots of other properties that are observed for real materials, but not properties of the SYK model. Anyway, that would be another big talk, and I won't go into it. But we are very excited about this progress. And of course, the question is, can this progress make a better superconductor? I don't know. That's the question we're still working on. So we made some progress. Okay. All right, so I'm out of time. Maybe I'm going to skip this part. I have to finish at 5:15? Okay, maybe for a few experts, let me quickly say a little bit about this pseudogap metal. What is this mysterious state over here? And I'll be quick, but actually it connects to the old picture of Kekule. So I go back to this antiferromagnetic insulator, where the spins were forming this square lattice with half of the spins up and half of the spins down. And now I have to change P. This is in the insulator where P is 0. So I have to remove, sorry, before I do that, this is what's seen in the real world. But in 1988, Bhaskaran and Anderson proposed maybe there's some other state we should think about, which is exactly the analog of Kekule's state, where these spins form entangled pairs, and then the pairs entangle each other. In Kekule, there were only 2 states. Here, there's an infinite number of entanglement possibilities. And then you have to make this into metal by removing some electrons. That's changing the value of P on the phase diagram. And then you get these empty sites which bind with the spins. And finally, you get a metallic state that we call FL star. And this turns out to be this particular state you're seeing here of entangled vacancies, spins, and electrons doing their dance that we proposed way back in 2004, which is actually fitting a lot of recent experiments. Okay, so let me just end there. So to recap, I took you through a very complicated journey. I'm sorry, but it's like the story of my life, really. But the common theme, the two common themes have been multi-particle entanglement. And there's a certain type of complex entanglement that appears when you have lots of particles moving around, which has this universal Planckian behavior. And that ties together, a wide variety of physical systems, and it led to, I think, significant progress in understanding black holes and also superconductors. So yeah, so the hero story, of course, is the SYK model, which describes multi-particle entanglement, resulting in Planckian dynamics and the loss of identity of particles, meaning the breakdown of the Sommerfeld theory. And these two really go together in this class of entangled models. And starting from this model, we have generalized it in a certain way that I haven't described, which gives you, in fact, we believe, a fairly complete understanding, and at least a starting point anyway, of this strange metal, including its Planckian relaxation. And this requires, for the cuprates, this new entangled metallic state at low doping, which we also think seems to be observed. And of course, but the question we have not answered is, can you understand, now that you understand this strange metal, why is TC so high? Okay, just wait, we're working on it, okay. And finally, as a bonus to us really, somehow these ideas had an impact on another field of physics where Planckian relaxation was present, which is black holes, for very different reasons. There it has to do with the quantum mechanics of gravity ripping apart these entangled pairs on the horizon of a black hole. And that leads to a very similar type of Thank you.
Yeah, no. Yeah, we can give another mic to.
It's turned off.
So thanks very much, Subir, for taking us through that very interesting cosmic kind of entanglement between black holes and superconductors. In some ways, it's, I think, a metaphor for physics itself, but you can't really separate theoretical physics into different disciplines. They're all entangled at some level. So I think you did an amazing job in conveying these very complex concepts to the broad audience. I'm sure there are questions from young people. We can take a few. Please don't be shy. Please, yeah, I see already. So to the young lady there, and then after that to the gentleman next to him.
Thank you very much, sir, for the talk. Actually, I have one question. You mentioned that if there are two pairs of electron, one is in India and one is in China. Let's suppose if one is in...
One pair.
That's okay, yeah, that is one pair. And let's suppose one electron is in the Earth and another electron is 2 light years away from the Earth.
Yeah.
So if we change the spin of the electron which is on the Earth, that means the spin would be changed of the electron which is 2 light years away from the Earth.
Yeah, this is exactly what Einstein didn't like. Yes, correct. This is what quantum mechanics says.
Okay,
Yes.
so that means that entanglement is rapid from the speed of light, or I mean.
Well, I mean, I think the conceptual point is that, yeah, the one thing you have, there's a quantum state that the two electrons share, and they share for this experiment to be successful. At some point, the two electrons had to be in the same place. you had to have them both in one room. They were talking to each other, and they formed this singlet, this entangled pair, and then you separated them. So when they form this, only focus on the spins. So we think of the spin of the electron as kind of distinct from their position. So there's a certain state of the spin of the electron, and that state is just there. It doesn't belong to this electron or that electron. It's not any particular place. So the concept of a quantum state is not associated with any location. But that's what you have to accept. That's what physics says. And so when I'm observing my electron and the other person in 2 light years away is observing their electron, nothing is going from me to them. They both just still belong to the same state. So we're both perturbing the same state, which is neither here nor there. No information in particular is going from me to them. So, I mean, this allows me to bring another point. So this does have some use. It does not have a use for transmitting information faster than the speed of light, which is what Einstein seemed to think it was doing. But it does have some use in transferring information securely. So for example, there's my friend in China, and I'm here, and I observe up, and then I know that my friend is observed down, for sure. So I can send a message to my friend. If you've observed up, then the Netherlands has won the game. And if you've observed down, then England has won the game. Now, somebody can eavesdrop on that message. They will not know what I'm trying to tell. Okay. So that message will travel the velocity of light and get there. And nobody could intercept that message and know what I was trying to say, except the person who received it. So that's the idea of quantum entanglement, allowing you to send information securely. That's the idea of behind quantum cryptography. Companies in Bangalore trying to explore this. You knew. But you cannot use entanglement to send information faster than the speed of light, for sure. If it did, then there'd be a problem. And then Einstein would be right. But in fact,
Thank you, sir.
Hello.
So there was a question next, there.
So, what is mean by independence in the case of electron? Like 2 electron will not interact.
Yeah, so of course, no, they're not independent.
Yeah, 2 electron is not dependent.
Yeah, they're
So
not independent.
what is mean by independent in this case?
Well, it was just a guess. So what Sommerfeld, electrons all interacting, but let me just ignore it.
Why?
And it works.
No, why?
Why does it work?
Yeah.
Well, you have to take.
No, why we ignoring this?
Because then we can solve. That's really all it was. You got this huge amount of electrons, and he said, I can't solve for, if they're all interacting with each other, it's impossible. So let me make the very simplest assumption that they're independent.
So
And then it works. Now, today we understand why that works. Well, I would have to, let me summarize. It again has to do with the exclusion principle.
Okay.
So the way it would fail if you have collisions between the electrons. So the collisions also have to obey the exclusion principle. So really what happens is that at a given energy, either all electron states are occupied or they're empty. So collisions are very rare. So it's the same reason that the Maxwell-Boltzmann theory of gas in this room works. Collisions between the molecules are very rare. It turns out that even for electrons, because of the exclusion principle, collisions are rare. So we understand well why Sommerfeld's bold proposal works today. Sommerfeld didn't quite understand it, was just a guess, and it worked. Today we understand that much better. So that's why it was such a surprise. Everything was looking good. Experiments worked, the theory worked. Sommerfeld could celebrate, and he could get his Nobel Prize eventually. Everything was great. And then these materials came on site where it just didn't work. And we didn't understand why. And that's what I've been trying to tell you. Our attempts at understanding why, in certain situations, you cannot ignore the interaction between the electrons. I
Okay.
mean, I just gave you a flavor of that in the very last part of my talk.
So the
Okay. Yeah, we should
so
probably
the
move on. I think we should move on. There are many other questions.
no, just is a follow-up of that. So the idea of
No,
No, please.
we should give a chance to other people also.
Sure.
I think yeah, there's a question here. I think, but before that, there are people online also. There are many people tuned in online, and there are several questions. Again, I can only pick a couple. So one interesting question by Raghav Manchanda is there a quantum phase transition in a black hole?
Yes, you can have different phases of black holes in various theories of quantum gravity, like string theory. In the real world, I think no one's ever seen one. Yeah, they're all basically the Schwarzschild black hole that Schwarzschild discovered in 1916. But there could be many other types of black holes, at least theoretically. Yeah.
Yeah. Yeah.
Yeah, Professor. Like my question is like rather a clarification on what you said. So you said like if I have a like an entangled pair, and if I put one inside, like one of the pair, like one of the particle in the pair inside the black hole, then the other will give me a random result, and that is where the entropy is like coming, and that is where the temperature is arising from.
Good
So-
summary.
Yeah, so if I have like two black holes, then like when they interact, they will some sort of like equilibrate, and that time scale is where the Planck's time scale is coming, and that is where the relation is being made with the
Okay,
SY
what
cube.
I really would like, I think, yeah, the good question. Let me clarify. What I really was talking was one black hole. Okay, so one black hole, if I could maybe throw a pebble into it and watch some waves on the surface of the black hole, which will slowly disappear and become a perfect sphere again. That's the experiment. That's the theoretical calculation I'm doing. Just perturbing a single black hole. Now, I don't know how to do that experiment in real world. So in real world, we look at what we can see, thanks to the magic of LIGO and other observatories. We can see two black holes merging into each other. So I showed you that picture of them merging.
Yes.
But eventually they become one black hole. And this universal timescale is really the very last stage of the merger. It's almost a sphere. It's just got some undulations on it. That's all I'm talking about. The only reason I mentioned two black holes because that's how you perturb a black hole. If I could find another way to perturb a black hole, of course, we would use that. This is what I should have turned that over to Rajesh. So a lot of people are working on that using SYK type models to understand the entanglement inside a black hole. That is, that's like the key problem, like computing TC in superconductors, understanding entanglement of black hole. That's the holy grail of these two fields.
Yeah, and we are still far from experimentally kind of probing that regime. I think we can make out these quasi-normal modes, like Subir said, which are kind of these ring-down modes, as they're called. But yeah, much deeper properties of entanglement, I think, can't. Yes.
So, like, since you touched upon the topic of quantum mechanics and superconducting, we know that like we are building trains which use superconduction. So does understanding the quantum part better, would it impact the technology that we can use to build trains which use superconducting technology?
You're asking, are theorists any use? Well, we certainly hope so. So I think the current status is that there's a short train in Shanghai from the airport, which uses superconducting magnets for levitation. And there's a much longer train under construction in Japan, but none of them actually use the high temperature superconductors. That's the next generation. So I think there are many engineering issues associated with these trains. And cooling the superconductor down to liquid nitrogen or even lower is not the most urgent thing. I mean, there are many other issues and costs associated with that. So let's see. I mean, I don't think the high TC materials, the cuprates, have not really been tried for that purpose. Where they are really making remarkable progress in recent years is in the fusion reactors and also in very compact power transmission. You can, when you're under a big city like New York, to transmit high density power to all the big buildings, you need a lot of copper cables. If you use superconducting cables, you can shrink that down dramatically. And that's something that seems to be really coming. Maybe we'll see that deployed in many places soon. Let's hope, yeah.
So I'll take one question here. I mean, I think you've sort of answered it, but let me say it anyway. Is it possible to transition from the SYK, presumably pattern of entanglement, to the standard Sommerfeld pattern by variations of parameters?
Yes, indeed. That is exactly. I was a bit quick at the end of my talk, but that is exactly what's happening here. Well, yeah, so that's exactly what's happening down there. So here we have the pseudo-gap metal where you have this entangled state, and in between you have the strange metal. And as you go from here to there, then you're going from SYK type entanglement to Sommerfeld type entanglement. And yeah, we understand some of that. That's the part we understand. What we don't understand is this point over there. That's the real challenge.
Okay. There's a question up there. We'll take just one or two more questions.
So what exactly are charged black holes?
Oh, good. Good point. I'm sorry. Yeah, that was there in one of the slides. Thank you. Charged black hole, basically, it's a black hole which has more negative than positive charges or vice versa. So electric charge. The electric charge, that's all. So most black holes are neutral. I mean, almost neutral, but they probably have, it's hard to get charged black holes because if you have a net charge, electrical forces are so much stronger than gravitational forces that if you had some star with a net charge, positive charge will be attracted and will neutralize it fairly quickly. But theoretically, it turns out charged black holes are a little easier to deal with. They're stable objects once they form. It's for such black holes that we understand a lot about the density of states. The density of states of neutral black holes is still sort of an open problem.
Sir, hello. Sir, below TC,
yes,
entanglement emerges and also the doping. And do we understand the physics of when and how entanglement emerges?
Yeah, that's a great question. The entanglement emerges in the strange metal, I should say, which is like the parent of the superconductor. And why is it there? Yeah, so what I think the message I gave here in the last part of my talk, it seems like near a quantum phase transition seems to be the best place to find lots of entanglement. And it's also true, yeah, thank you, that's a great question. It's also true that almost any interesting superconductor today with a high critical temperature is near a quantum phase transition and also displays a strange metal. So these ideas kind of are consistent with each other in that sense.
One question again online from Mudit Chaturvedi. In your current research, where do you see the most urgent need? Do you see, I guess, the most an urgent need for computational breakthroughs and perhaps using machine learning to find ground states? Are we entirely dependent on waiting for scalable quantum hardware to simulate these models?
Oh, that's an amazingly good question. So there's many levels to it. Yes, absolutely. Numerical work is becoming more and more important in understanding a lot of these complex systems. I mean, the SYK model was, it's a toy model. It's not the actual model, but if we want to understand quantitatively something realistic, we will need numerical computational work. But with traditional computers, there's something called a sign problem. It's not so easy to to simulate this exclusion principle of electrons in a computer, even in principle. But there has been tremendous progress in that direction just in the last couple of years using machine learning methods. I'm very actively involved in them. So another possible route to solving these complex entanglement problems would be to use quantum computers. Well, almost essentially every quantum computer out there is a quantum computer of bosons. It has spins. It doesn't have fermions moving around. So I am a bit skeptical that quantum computers will, at least the way I constructed today, will tell us much about the states relevant to these superconductors. They may tell us more about other states and other materials, but for this particular problem, at least the bosonic quantum computers, this is not a popular point of view. I might be shot pretty soon by some of the people in quantum computing, but I don't think they will, really.
Okay, good. Well, I think it's a question that maybe we'll take that as the last question, I think.
Sir, I have a thought experiment type question. You were talking about the entangled pair of electrons, right? One in
Yes.
China, one in India. Sir, let's say there was a game where you know that the electrons are entangled. One is in China, one is in India. And the China electron, let's say the host has hid it somewhere randomly and you do not know the position. But can you in any way from India find the position of the entangled pair of electrons? Or what
No,
happens in
no,
that case?
I mean, it depends a little bit on what you mean by entanglement. I was just talking about a very simple type of entanglement in the spin of the electron. So by definition, position is not involved at all. But there can be a more complex type of entanglement where position is involved. And that is, in fact, partly what the SYK model succeeds in doing, is things are moving around there. So at least in the SYK type of complex entanglement, position is also entangled. And that's partly what makes it so interesting. Yeah, but then it's a million particles and you never know you only have statistical information of the state. So the answer is no, basically.
Okay, last one from St. Joseph's for old times.
So recently there has been an experiment which has measured attosecond long interactions of entanglement between electrons when a hydrogen molecule was excited by a laser beam. Do you think this could be of any relevance to computational models regarding entanglement?
I'm not aware of this experiment, but I would say that's more a remarkable experimental achievement than something theoretically non-trivial, because already in the 1930s, we knew everything we needed to know about entanglement in a hydrogen molecule. That's completely well understood. It's not. In terms of conceptual theory, there's really no uncertainties there. But as doing it, measuring it on such a short time scale in a single molecule, that's an amazing experimental achievement. But as far as I know, they have not seen any contradiction with the long existing theory.
Okay.
So I have a small doubt. I was asking that how the electrons of low densities are removed from the antiferromagnetic.
Oh, perfect. This is the true chemist. How do you remove the electron from the antiferromagnetic? Excellent. So you see this little X here below the oxygen, 6 plus X. You just have to remove some of the oxygen. So you do some electrochemistry. Don't ask me how. And
No issue.
their oxygens are sitting outside somewhere, and you just remove them, and that changes the charge density on these layers. In fact, that's a great question, because there's many materials we think could be very good superconductors, but we don't know how to change P for them. Nobody has succeeded in doing it. So this is almost alchemy. This is where the complicated chemistry of the whole crystal comes in. For some mysterious reason, in these materials, you can change P very readily.
Okay, sir. And one more thing, sir.
Yeah.
Actually not I, we from our school, we want to address you, that you address our school, KV PM Shri KVASC, to our students too in the school.
Okay.
We are inviting you to the school actually.
Let's talk about that later. Thank you.
Okay, sir.
Yeah.
No issues, sir. No issues.
Subir will
Thank
be
you, sir.
back, so if not this time, I'm sure another time. So let's conclude by thanking Subir again for a very enlightening and very stimulating talk. And on behalf of ICTS, there's a small new kind of a memento we are presenting our speakers. This is with an organization called 14 Trees. So they have planted a tree in the name of Subir in their campus in outside Pune. And actually there is a QR code which you can scan and actually see your tree grow. And so the idea of 14 Trees is that if we plant 14 trees in our lifetime, we some ways offset our carbon footprint. So, so this is a very nice organization that we have paired up with. And so I forgot to mention for Vidya also, I think you have a tree planted in your name too, Vidya. So, and your trees will be entangled, I suppose, with each other. So in any case, thank you everyone for joining. Please come outside for high tea and hope to see you all again at ICTS.